My name is Talip. I'm the founder of and CTO of Hazelcast. So we'll be talking about in-memory data grid, distributed caching, NoSQL, all the fun stuff today. Let me start with actually with a little more background. So in 2004, I posted this weblog and I talked about distributed hash tables and how they can be implemented. I was quite inspired by Doug Lee's concurrent hash map and how he used segments and I thought about like how this segments idea could be implemented in distributed way. So that was the start of the whole thing actually for me. So 2004, and then in 2008, I posted this weblog and I said, hey, Hazelcast 1.0 is released, and the idea was that if we provide distributed data structures like queues and maps and locks, and also provide distributed processing services like executor service, MapReduce, and entry processor, things like that. So then the developer can mix and match and build custom distributed applications. Because essentially, when you're building an application, you use functions, processing units, right? And also you use data structures like maps and queues. So if you made those things in distributed way, then you can build distributed applications. So we don't dictate how you implement this stuff. We give you the primitives like the maps and queues and executor services. So and also since I'm a developer, I don't like complexity. I said like, hey, it should be super simple. It should not depend on any other jar. So it should be a single jar and very lightweight. You put a jar into your class bed. You start using the distributed primitives and build your application easily. So that was the motivation. So June 30th, 2008, a little more than 6 years ago. So that's a long time. Okay, so after history, so what are we talking about here? Let's start with the basics. So you know this is hash map, and it's not concurrent. It's not thread safe. You cannot share that this hash map across multiple JVMs. If you want to, use concurrent hash map. Now it's okay to share this map across multiple threads because it is thread safe. So what if you want to share the map across multiple JVMs, not only threads but multiple JVMs? So this is what Hazelcast does. So you create a Hazelcast instance with a configuration instance, or you use XML file to define your configuration, and then once you have the Hazelcast instance, you create Hazelcast map. Now, as long as names are the same, you're actually working on the exact same map across multiple JVMs. All JVMs are going to be working on the exact same map. The entries are going to be shared and synchronized across multiple JVMs. So that's the idea. So I'll do a quick demo, to give you the feeling, and we'll dive into the details a little bit. So when you unzip Hazelcast, you're going to see a directory structure like this. We have map center WAR file, and you can put it into any your favorite web application, web server like Tomcat or Jetty or WebLogic. And then so you can monitor and manage your cluster. So I did that already, so I put it into my Tomcat, so I have it on Tomcat 6 web apps. I have it here, so I have that WAR file copied here. So I'll start my Tomcat actually, so that I can visualize my cluster. So okay, Sage started Sage. My Tomcat started, so my management center is running right now. So okay. So in the lib directory, we have several jars. These are all Hazelcast jars, and Hazelcast. This one is the core Hazelcast server jar. This is client. This is for AWS, and this is for Hibernate second level caching. This is for exe transactions. And Spring integration and web session clustering. So, but Hazelcast all contains all of it. So take that jar, put it into your class path, you're ready to code. So that's all you need. So just take Hazelcast all jar, put it into your class path. So, and I built a command line application to demo Hazelcast. So I'm going to run that application quickly here. So it's very simple. So let me actually show you what it is. So as you can see, it says, "Hey, start Java, run this test application here, and use this jar file." That's it. So it's a command line application. I'll run and play with it a little bit. So it says, hey, I started the node on this IP with this port. There's only one member in the cluster, and that's me. So that's good. So in the configuration, I also changed one single thing only, nothing else. I said, hey, because I was running Management Center, so I enabled Management Center. And I said, hey, this is the URL for the management center. So Hazelcast node will push all its statistics to this URL, and we'll be talking to management center via this URL. So we enabled that already. So it's connected right now, and we should be able to see that. Here, right? So it says Hazelcast will connect to Management Center. That's good. So if I say map, so we're working on the default namespace, default map. That's the name of the map. So m.put1. I'm from Istanbul, so I'll put Istanbul here. So as the value. So 1 Istanbul m.get1 returns you the value. So, okay, so this is just a map put and get. So let's visualize that. So let's go to the management center actually and see how things look from there. So I log in, admin, that's the default password, no need for this. I'll connect to the dev cluster, yes. Okay, we see only one member in the cluster, and this is the default map that we've been working on. There's only one entry in this map. That's fine. So let's put more. Put many. I'll put 1,000 entries in one shot. So and that size should give me 1,001. So if I go here, that should get updated and it should tell me that we have 1,001. Yes. So I'll start the second node and you'll see how things are actually distributed. So run a Sage. I'm starting the second node. So you can just imagine that you're starting a same application on another machine in the network. So these guys are going to be using multicast to discover each other and form the cluster of 2 nodes. Great. So we have 2-node cluster right now. and this says, hey, this is my IP and this is my port. We are a 2-node cluster right now. That's fine. So if m.size, map.size, basically gives me the same value. And on my management center, I see that we have 2-node, and on the entries column, you see that so they're now almost equally sharded. So if you look at the backups column, actually you can see that these guys are actually backed up here, and these are here on another. So the entries are backed up on the other node. So that's expected. So we have one backup as the default configuration for this map. So that's why we have 1001 entries and 1001 backups. So let's start the third node and see how things change. SH run SH, and this guy will use multicast, and by default, it doesn't have to be. And join the cluster, and you should see the third one coming up here. Yes, I see the third one here. Okay, and since we didn't have millions of entries, the redistribution or rebalancing was super fast, and now we see that these guys have about 300 entries each. And if you look at the backups, total is the same, still 1001, but I noticed that so there's no like 298 anywhere in the backups, because so the way backups work is not like one node is the backup of another one. So it's not like that. So so these entries are actually backed up onto two other guys here. So some of them are here and some of them are here. So the same goes for the second node. So second node is actually backed up onto first and third nodes. So the reason why we do it this way is that backups are actually right now balanced. So if I lose the first node, I don't have to rebalance the cluster, because the backups are going to be owned by the other two guys, and I'm already in a balanced situation. So I don't have to rebalance. But of course, backups, I lost backup, so I'll have to take backup. But so when you lose a node, you're already you're already suffering from losing a node, right? So if you then we should not be worried about rebalancing the cluster because you lost a node. That's why Hazelcast is ready to lose a node. So it's backups are distributed evenly onto the other guys, so that you don't have to worry about rebalancing after crashing. So, okay, so we extended the map so that we can do more with Hazelcast. So, like, we support locking and listeners events. So if I log entry 1 from here, so so this node has a lock on this particular entry in this map. So if I try to update the key 1 here from here, and I live in Palo Alto, so I'm not able to, because this guy has a lock on the key. So, but watch, as soon as I unlock the key 1, you'll see that update goes through. So also you can add listeners so that you can listen for the map events. If somebody else adds another record, so this guy will get notified. So notice that. So this guy was only guy listening for the for the updates, and the event says, hey, this key 2 with the value London is added by this member. So we know what happened in which map, and who made this happen, right? So who initialized the event, right? So that's good. So so idea was not only distributed map, of course, but also other data structures like queues and topics. So queue is a Java util blocking queue implementation. So let's say this node is trying to take tasks from the tasks queue or default queue and process. So, and it happens to be that, let's say, this node receives the receives a request from the user and creates and offers a task into the queue. So task is offered by one JVM, and it's taken by another JVM and processed by another JVM, which is nice. So if two guys are trying to take Q.take, should say, Q.take, and if I'm offering only one, Q.offer task 2, only one of them will take it, and the other one is still waiting, right? So just like a regular Java util concurrent blocking queue. And now I offered the third one. Now everybody took one and processed. Nice. So the topics are a little different, just like JMS topics. It's a pub/sub messaging. So let's say this guy is listening for the messages, but also this guy is listening for the messages. So you can anyone can listen on the topic, and anyone can publish. So let's say this guy is publishing a message. Yes, let's say we're publishing a message. All right, so as soon as I published a message, since we had two guys listening, both received the message. So that's how it works in pub/sub. So it's a little different than the queue. So queue, only one guy takes it. Topic, whoever listening will get the message. All right. So I think you got the idea. So there are many other data structures like atomic long, MultiMap. So what we'll go over the examples and we'll see some of it. All right. So let's go back to the presentation. All right. So we started the instance, Hazelcast instance. This is like a this is the embedded node, and then you got the map and you started working with the map, just like you would do with the Java util map, right? It's very simple. You don't have to put strings, of course. you put regular objects into the map. But the objects should be serializable because we rely on serialization. We serialize the entries across and serialize the entries and send them across the wire. So serialization is important. So why Hazelcast? Because applications want to share state or sessions like HTTP sessions or any custom sessions that the application has. Usually they want to cache data because they don't want to go to the database all the time. And distributed caching is a little different than local caching in the sense that like the local caches are going to be super fast because there's no networking involved. Distributed cachings are going to be slower than local caches because networking is involved, but it gives you the consistency across multiple JVMs, right? So any update happens in the cache will be seen by all the other JVMs. So in the local case, local cache scenario, you don't have that consistency. So every JVM has its own copy, and it could be out of date. The messaging. So as we saw in the queues and topics, you can send and receive messages, or you can have producer consumer pattern. So in many cases, whenever you need messaging, you use a JMS solution like ActiveMQ. What we're saying is that 90% of the time, an embedded Hazelcast messaging will be just fine for you. Why do you want to run a separate ActiveMQ or a messaging process and maintain that process, right? Embedded into the application and don't maintain any other separate process. So, but of course, we're not complete messaging solution too. We're not, for example, messages. We don't guarantee this stuff. Some of the things that other messaging solutions guarantees. But 90% of the time, the JMS queue, the Hazelcast queue and topics are going to be exactly what you need. And if you need more than that, of course, go consider using other messaging solutions. Distributed processing with the distributed executor service and MapReduce, we allow you to process on multiple JVMs. So that's why, I mean, how and why Hazelcast is used. So Hazelcast is Apache. It's about 3 megabyte jar. There's no dependency. You put the jar into your ClassPad, you're good to go. Nothing else is needed. Out of box, you'll get distributed maps and queues and sets and logs and a lot of other data structures and also processing services like executor service, MapReduce. We do have native Java, C#, and C++ clients. And also we do support REST and Memcache. If you want to learn more about the cluster, use the clustering API. So how does it work? How do we partition the data? So we have default 271 virtual partitions. Keys are going to fall into one of these partitions. The calculation is actually very simple. We just convert the key into byte array, hash it, and mod with the partition count. Since since the hashing of the byte array will be the same, and since we have the partition count fixed, the partition ID will be exactly the same for a given key all the time. So so now we know the partition ID for the key, and partitions are owned by the nodes, and every node knows who owns which partition. So when you do a map.put, we take the key, hash it, mod with the partition count, we get the partition ID, and then we say we go to our internal lookup table and say, hey, who owns that partition? Which node owns that partition? Is that me? If it is the local node owning the partition, then it will be a local operation. But if it is very possible and very likely that it will be some other JVM owning the partition, then the request will be serialized and sent over the wire to the owner node. An owner node will process the put or all the other key or partition-aware operations. Okay, so so if you have 10 million entries, and if you have 10 nodes, then each node will own a million entries, so 1/10 of the entries. And also some number of backups. So let's say all of your maps have only one backup. That means each node will have 1 million owned and 1 million backup entries stored. So it's a fully partitioned, fully sharded system. So as you have more data, you add more nodes to scale. That's how it's done. So adding a node means migration. So some of the entries, or actually some of the partitions, will migrate to the new node. Since we have the keys or entries or data in those partitions, all those entries are going to be migrating to the new node. So you can say, so it's a fully partitioned system, and Hazelcast knows about the partitions, not the entries, and partitions will move around as you add or remove nodes. So when you lose a new node, for example, when you lose the node, backups are going to be owned by the backup nodes, and system will continue running without losing data. That's, of course, so it depends on, so losing data depends on the number of backups you have for the maps or queues. So if you can configure the map to have no backup, for example, or you can have one backup only, and if you have two nodes crashing, then you do lose data because you only had one backup. One backup means one owner and one backup. So 2 copies of the same data available in the cluster. So Hazelcast is thread safe. So you don't have to synchronize on the Hazelcast object or map object that you get from the map. So all operations, puts and gets and everything, every Hazelcast API call is thread safe. So you can create multiple Hazelcast nodes on the same JVM. So this is going to be starting one node. One node means actually it will have its own socket, it will have its own threads and everything. It's a totally separate instance, and this guy will be starting the second node. Now, if you run this code, you'll have 2-node cluster. So you can write a JUnit test containing 5 nodes, for example, and assert your assumption. So that's also we have something we have to use internally to test our stuff, right? In a JUnit we start multiple JVMs and we test the end-to-end behavior of the cluster. So as I said, we rely on serialization. So the entries or objects that you put into the cluster they don't have to be really serializable, but somehow they have to be serialized. I mean, either the entries are going to be serializable themselves, or you provide a serializer for those. So 2 choices. So you got either the entry itself or value itself serializable, or you provided a serializer for that entry. So the biggest cost in distributed systems like this is actually the serialization, not the network. Network is pretty fast. Serialization will slow it down significantly. So I highly recommend you optimize your serialization first. We provide data serializable, very simple interface to make things a little faster. We have even a lot of other ways to make deserialization faster, and even more portable too. So portable serialization will give you will allow you to serialize your Java, C#, and C++ objects in the cluster. So that's a big topic to cover. But I'm just let me remind you that this is one of the biggest costs in distributed computing. So make sure you take care of the serialization very well. So if you want to know about your cluster, like how many nodes do I have, or who I am in the cluster, or so you want to listen for the members joining or leaving the cluster. So we have an API for that already. So distributed map, we talked about that. So it's actually a concurrent map. So Java is a concurrent map. That means you can do put if absent and replace. These are amazingly good APIs. So I highly recommend taking advantage of these atomic calls. I mean, the cost is higher when things are distributed. So if there's a way to do things atomically, do it. Take advantage of that. So put if absent is one of those things, for example. MultiMap is a specialized map. It's a one key mapping to multiple entries. So as you can see here, so the same key is used for 3 put operations, and when you do a get for the key 1, you get a collection of these entries. So one key, multiple value. So the main inspiration for this one was the Guava library, and it had MultiMap as part of their collection. So I really loved it. So and implemented distributed MultiMap for that reason. So distributed queue, it's a blocking queue. So we support all the timed operations like offer with 500 milliseconds, or poll in 5 seconds. So these are very handy because sometimes you don't want to wait infinitely. So you just want to say, hey, if I get something in 5 seconds, I'll execute. Otherwise, I have other things to do. Distributed logs. So we have Hazelcast get log will give you the Java concurrent log API, and it will work just like you would expect. So only one JVM, one thread in the entire cluster can own the log and execute, and finally has to, of course, unlock it. But maps also do have logs. But these, like when you log a key 1 in the customer's map, you're only locking that entry in this map. So locking key 1 has nothing to do with other maps, for example. So you're just locking this specific entry in this specific map. So that's the granularity of the log. So when you're so that means all the other keys in this map also is not affected by this lock operation. So they're lock free right now. So only you're locking key 1. Make sure you unlock, of course, finally when you're done with it. So we do have, of course, timeout for the logs also. So if we extended the API a little, so that we can, the timed operations are very nice in distributed, and I think it's important too in distributed systems, because you don't really know. So it's not one node or one process that we're talking about. We're talking about multiple. We're talking about 50 JVMs doing something together, and you don't know what the other guy is doing. You may not want to wait like infinitely, and you just to be safe, you may also want to set a timeout for the lock in case lock is not released properly. So timeouts are or TTLs also very important for the distributed operations. Okay, so topic, just like we talked about it, just like JMS topic, this code will compile and run just fine, assuming that you have the Hazelcast instance defined earlier. So you say, hey, sample class implements message listener, so that means you have to implement on message. And you add the listener, anyone can publish, and so whoever is listening for this topic will get a message and actually Hazelcast will call your own message a method and pass the message out to you. So it is you can use it as like imagine that let's say you wanna a centralized logging. So all nodes are gonna publish the logs into the logs topic, and one guy in the cluster will consume or listen for these log events and log them locally. So everybody publishes, only one guy consumes, or one or two guys consumes. Maybe if you want to have a like redundancy in the logging. So that could be one use case, or you want to notify everybody, every node in the cluster that something happened, and you want them to take action. It's very simple mechanism. So just put the Hazelcast jar in, create your topic, and anyone can listen and publish. Events we saw in the demo. So you can listen for the map events, and you can Hazelcast will call you when entry is added, removed, or updated. Also, when the entry is evicted, but I didn't put the example here, just to keep it brief. So transactions, we do support local and two-phase commit. So here's an example of two-phase commit for two-phase transaction. So you create the transaction options. You say that it's two-phase commit, two-phase transaction. You create a context, and then from that context, you get the transactional map and queue. So transactional map doesn't have all the operations, all the function API that the IMAP or Hazelcast map has. So we support a subset of IMAP operations in a transactional way. So you get all these transactional maps and queues, and you can pull something from the queue and process it and put it into the map. And when you're done, you commit the transaction. So this ensures that all these operations will happen or happen entirely, or none of them will happen at all. So all or nothing, right? So since you're using multiple data structures, and these are all distributed operations, two-phase commit makes sense. But two-phase commit is also, or transactions in general, very expensive. So you have locks on the entries, or you have you lease resources in the data structures, and you have to go through multiple steps to commit or do the update or commit your transaction. So it's costly operation, and it will be more costly when you have contention. So there are two aspects of the transaction actually. One, so yes, latency will be higher, which is fine sometimes. Like, okay, I'm okay with like being 3 times slower, but it will be transactional, which is good. So this will happen. It will be 3 times only if you have no contention at all. So like you're only updating different entries. You're working on different maps. No one is waiting on somebody else's lock or entry. So that's fine. So you will just suffer from the latency issue, which is, I mean, not a big issue. But when the contention is high, then the system can be very, very slow. So, but this is very general distributed transaction or transaction problem. It's not specific to Hazelcast at all. Just be careful. That's my that's my suggestion. So just make sure that you really need transactions. I mean, justify your use case first. So data affinity. So when you do as I said, the maps are sharded based on the keys, not the map names or anything like that. So the keys, we use a key for a data structure. For the map, we use the key of the entry. For the queues, we use the name of the queue as the partitioning key. So even though these, in this example, even though these maps are different maps, map A, B, C, since they are working on the same key 1, they're actually they're working on the same partition, which means same node. So all these keys are going to be on the same node because the key is the same. We don't care about the map name. So when you do a lock on the key 1, again, we use the key to define the owner of the key. So that means all these guys are going to be running on all these operations are going to be on the same node. So this is a distributed call. Again, so distributed call says, hey, run me on key 1. That means this distributed execution will happen on the same node also. So all of these guys are going to be will be executed on the same node because the keys are the same. So what if, let's say we have 2 different maps, customers and orders, and we have customer ID is 1, and this customer has 3 orders, 21, 22, and 23, so different orders. So since we look at the keys, so it's very likely that they're going to end up on different nodes. So even though they are related, they still they're not on the same server. They're distributed. So how do we make sure that the customer orders stored on the same node as the customer? So you come up with the order key and you make it partition aware, and implement get partition key because it is partition aware, and you say, hey, customer ID is my partition key. So if you do that, then when you do customer put 1 and then you insert 3 orders with this order key, Hazelcast, since the order key is partition aware, Hazelcast will look at your partition key, which is 1, and it will make sure that these entries are stored on the same node as this entry. So customer and its orders are going to be stored on the same node. Executor service. It's a very regular Java util callable stuff. So you implement call and you turn value. But you make it serializable because we're going to serialize this call across the wire, right? So you say, Hazelcast, give me a service, execute service, and then you submit a task, and then it returns you the feature just like in the API. So and then when you're ready, you say, hey, give me the result. So this task will run in the Hazelcast cluster. That's how. So that's the difference. I mean, other than that, I mean, you're using the exact same Java util concurrent execute service API. This is Java util concurrent feature, but the execution will happen in the cluster. Where in the cluster? So if you say, hey, this is a distributed task, I want that hello task to run on this specific member, then Hazelcast will run the task on this guy only. If you say, hey, run my task on this key, then Hazelcast will find the owner of this key and run that task on that owner node. All right. Just want to make sure that I have. So the questions, I started reading those. So let me see. Okay. So the first question, are the data structures read-only? No, it's read and write. Yes, there's a concept of write behind, and we'll talk about that just in a couple of minutes. What's the exact feature missing in the messaging on Hazelcast? So first, the persistence of the messages is missing. For example, the Hazelcast data structures are in-memory data structures. You can define a store to store these messages, but it's not as native as a JMS solution that stores the messages on disk and synchronizes with disk, and also and the listeners or the consumers are not durable in Hazelcast. So in JMS you can have durable consumers, and in Hazelcast you cannot. So let's say in the case of topic, let's say you have 5 listeners active and on like a 50-node cluster, and message is published and 5 of them will receive. And let's say one of the listeners died, and now we have 4 left, and a message comes in. We'll deliver the message to the 4 nodes, 4 listeners only, and we won't wait for your 5th to come up and receive the message. The messages are not going to be durable, and so topic messages especially, they're not durable, and whoever is available at the time of the message will receive it, others won't. So there are different differences like that. Yes, yes, we do have C. Is there a C++ based client for Hazelcast? Yes. Also for C# too. These are native clients. So it's not like we don't use a wrapper. It's strictly built with C++ and C# directly. So what's the ideal replication factor for the entries? It depends. So there are maps. There will be maps for you that you don't care to have any replica at all. You're going to say, hey, this map, I'm okay. I have a permanent store, a database, for example, already for the entries in the map. So I don't even care to have any replica at all, because for you, space might be more important than redundancy, because you already have everything in database. For another map, you can say, hey, this map is very significant. I mean, more important. I should have at least one backup, because if one node crashes, at least I can continue with the other with my operations without going to any other data source like database. So, for example, if you have heavy and like a big caching use case, and there are systems like you cannot even wait for the cache to warm up. So for those cases, you say, hey, at least I have to have one backup, so that I don't have to warm up my cache if I lose a node. And there will be other cases like you need more than one backup. Like there will be maps that are so important for you that you'll say, hey, I want at least 2 synchronous backup. By the way, you can have synchronous and asynchronous backups mixed and matched. So you can say, I want for this map to have 1 synchronous and 1 asynchronous backup. So so is there a concept of access affinity? What's let me see, say node. That is, if access is often from the same JVM node and the partition is on another one, instead of having the object serialized, deserialized all the time, we do a repartitioning to bring the object to the to the node. Okay, so okay. No, as of today, we don't. So the question is like, if I'm using this the entries a lot from one JVM, which is not the owner JVM, can I bring and can I own these entries so that I don't have to go across the network? No, partitioning is not going to look at your access pattern. Even though you're reading the entries the most, more than everybody else, you'll still have to access remotely. What you can do is actually enable near caching, and you can cache on the caller. That way, you don't have to you don't have to go across the network to get the entries, because it's nearly cached. But it's still a cache. It's not the owner owned entries. So owner will maintain the consistency, and the caller, frequent caller, will have a near cache of the data. So, and when you say cache, it is very possible that it is state. How does Hazelcast serialize efficiently for large data? So when you say, I mean, I'm thinking that you're talking about megabytes of. So if you're talking about like a per entry large data, then we don't, but we do plan to use compression of the entries. We don't do it yet, but we should be able to do it. We've talked about it, but it's not done yet. If you're talking about like per JVM having like gigabytes of data, like tens of gigabytes of data, and in this case, we do support off-heap storage, and we can store off the heap so that we can store more data per JVM. And when it comes to migration, we zip the entire partition and send it across the wire in one shot. But I'm assuming that the question is mostly about one entry being very large. So we should work on the compression. The locking for maps works for the multi-valued maps as well. Yes. For the distributed topic is message. Okay. So it's a configuration issue. So for the topics. So there are two things there. When you say, so the question, let me repeat the question again. For the distributed topic, is message ordering guaranteed? So if you look at the sender's or publisher's perspective, it's always going to be ordered. But if you look at the entire topic perspective, like one topic, and you have multiple listeners, and how do we guarantee that all listeners are receiving the topic or messages in the same order? So if the listener 1 receives the message A, B, C, D, how can we guarantee that the listener 2 also receives the exact same message in the exact same order, A, B, C, D? So it's a configuration that you have to set. You say this topic is ordered, and then we'll guarantee that that the messages are going to be delivered in order. No, there is no Python client yet. We're hoping that one of you guys will implement it for us. Serialization is pluggable, so you can plug your cryo serialization or protobuf or any your favorite serialization mechanism to Hazelcast. You don't have to use Hazelcast serialization at all. It's all pluggable as of version 3. So for large object graphs, we do. I mean, I highly recommend data serializable, or even better, identifiable data serializable, which is faster than data serializable. That way, so not that we serialize faster. We're actually asking you to tell us how your objects are serialized, so that because you know your objects better than JVM, so you can skip all the overhead the regular Java serialization will have to do. So that's why it's faster. So if the object is very large and complex, and then actually can get up to 100 times speed with custom serialization. How does sharding avoid hot spotting? Yeah, like it is very possible that, let's say you're building a financial application, and somehow Apple is on one JVM, Apple stock is on one JVM, and together with so many other stocks, and there's something happening with Apple, and people's going crazy buying Apple stocks, right? So one JVM will receive the majority of the requests because it contains the Apple stock. So obviously, one JVM will be really hot. The other JVMs are going to be not really But so the main problem here is not really how can we obviously Apple stock or is going to be on one JVM, and it has to be ordered probably by one JVM if the ordering is important. If ordering is not important, of course you can handle all these operations by multiple JVMs. But the biggest problem here is that, unfortunately, since everything is key based and sharded dynamically, it is very possible that you have other stocks next to Apple on the same machine, and other stocks are going to be suffering because of the Apple high load, right? So others are going to be ignored, or because you have too much things only for coming for Apple. So unfortunately, there is no answer for that yet in Hazelcast. This will happen because sharding is dynamic and it's not customizable. It is possible that one JVM receives the majority of the requests. So it is possible, but it's also a rare case too. It's not like most of the applications won't have that problem, but there will be applications suffering from the hotspot. When Hazelcast is run within the application, how does one control the memory settings for Hazelcast? Okay, so that's so when you run Hazelcast and embed it into the application, it's hard to isolate your application and Hazelcast if you're not using off-heap, of course, because if Hazelcast and also your application both on the same heap, when a GC happens, everybody or when any out of memory issue will affect both, and it's so hard to say who caused what, right? The isolation is so bad. But if you use off-heap, which is Enterprise Edition feature, then you can say, hey Hazelcast, I give you 10 gigabyte memory. Don't touch the heap. Don't store anything on the heap. That way you can say application uses the heap, Hazelcast uses the off-heap for storing data. So other than that, there is no mechanism on heap to make sure that we can isolate or separate the memory usage. So, and does the type of the data, the question is, does the, type of the data structure where the object ends up relevant on what serialization strategy is used? Objects representing messages on the topics versus objects represent, So as I said, so per data structure, okay, but this question is mostly about serialization strategy. Trying to understand exactly what the question is. Does the okay, no, the I don't think serialization will impact how data is sharded much. I mean, of course, we do serialize first and then hash it and define the owner partition, but it's so you don't have to think about like, hey, should I use that kind of serialization mechanism to make sure that the data will end up at this specific node or not. So I don't think you should think about serialization. You should mix serialization with partitioning, and you should. I don't think you should try to fix partitioning with serialization. These are two different separate concerns to me. So the tasks, what's the prerequisite for tasks to run in distributed node? So first, tasks has to be serializable. The second, the task code has to be available on the JVM, on the distributed cluster. So we don't serialize the so the tasks classes should be available in the class bed of the nodes. That's the answer, and the task has to be serializable too. So that's the okay. Another one. Yeah. So how do I shut down the JVMs for maintenance in a way that you will avoid losing data? The upgrades or restarting the cluster is right now a big concern for Hazelcast, and we're working on it. So of course, rolling upgrades are is very possible. You can shut down one node and start upgrade the node and start it again. And shut down the second node, start third, shut down and start. You can do it. You can do it like that. But how do you make sure when you can do it? You can do that. Like, how do you make sure that you can shut down another node? Because how do you make sure that the backups are taken properly and now it's safe to shut down a node? So that's the real question. So how do we ensure that it is okay to shut down and restart the node? We're working on an API to tell you when it's okay to shut down a node and when it's safe to shut down a node, so they can do a rolling upgrade. And also we started looking into persistence more deeply, so that we can take a snapshot of the cluster, persist on the disk, and reboot the cluster with the state again without losing any data, and make it super fast. So that's but that's on the roadmap. So we're working on it. Okay, so can we persist data stored in Hazelcast maps? Yes. So let me continue with the presentation quickly. We're already so it's already 10:09. So let me finish up the presentation and then answer the questions. So the query, you can query Hazelcast entries, map entries, and you can also index them. So if you have customers with these fields, you should be able to index those, and also you should be able to run SQL-like query. Hey, give me all the customers active and age less than 30. So this is pretty much like a SQL where clause. Persistence. Hazelcast doesn't persist your data, but if you implement map store, then we can call you to store the entries in the map. Same goes for the queues. So you can persist your queues, but you should implement how the entries are going to be persisted to the database. So basically, when we do when someone calls map.put, if you have a map store configured, we'll call your store key value. We'll pass you the key and value. You save that entry into the database. You can use Hibernate, SQL. You can talk to an Oracle MySQL or NoSQL database and store the entry. So when you do a map.get, when we don't have it in the database in memory, we're gonna call your load method. We're gonna ask you to load the key from that data store, from that database. So, so you will pass you the key. You'll go and fetch it from your MySQL, Oracle, or NoSQL database. And the persistence can be in asynchronously or synchronously. So if it is right behind, what this means is that put will return without storing the entry into the database, without calling map store. Hazelcast will just mark the entry as dirty so that it can be flushed to the database later on. If you say that if the map store is right through, then the put will happen in memory on the owner node. Also, owner node will call your map store implementation to persist or store the entry into the data store maps database. So you make a decision on the right behind or right through strategy per map. So one map can be right behind, another map can be right through. The configuration, so you can have multiple different groups or clusters: dev 2, production 2, application 1, application 2, and you can set up. We have many properties like Hazelcast initial minimum cluster size. So that means nodes are not going to start until you have 8 nodes. So everything will stop and wait for you to have minimum cluster size of 8. Or you enable ping protocol or ICMP so that we can detect the dead node faster. So you can have many properties, and properties are listed on the documentation. In network side, you can have multicast and TCP/IP for discovery, for join. So multicast is only used for the discovery. After the discovery is done, multicast is not used. Everything is TCP/IP. So all maps and queue and topic operations are actually TCP/IP with NIVIO, of course. All right, so interfaces will define which IP to bind when Hazelcast start. So make sure that Hazelcast starts on the right IP, and so that the nodes can talk to each other properly. Per map, you define backup count, asynchronous backup count also, if you want. Time to live for the entries, so that you can use it as a cache, right? Max idle seconds or max size for the map, so that the eviction can kick in when the max size is reached. And we can also define a map store, as we talked about in the persistence section. So per map, you can define different backups and TTLs and things. And you don't have to define all of your maps. So you can, Hazelcast will create the maps on demand. So as you ask for maps, it will create the maps on the fly. But you can use the wildcard configuration to say, hey, for all the maps starting with com Hazel, I want to use this configuration. So that way, so you can simplify configuration. So yeah, Hazelcast is a distributed implementation of maps and queues and so many other data structures and processing services. We do, Hazelcast has native Java, C++, and C# clients. And the clustering is dynamic. The failover and backup, they are all dynamic. So thank you so much for listening, for joining.